When we've worked with trigonometry in the past, we've been in the situation where we've always had a right angle triangle, either one that's sort of implicitly there in the diagram or one that we've been able to pull out by splitting our shape up or by looking for lines of symmetry. However, a lot of the time we're not going to have right angle triangles. So things like our sine ratio, so sine x is the opposite over hypotenuse, cosine x is adjacent over hypotenuse, and tan x is the opposite over adjacent. These rules, they still hold true. They're still something we need to know, but in situations like this, where we've got a non-right angle triangle, they are not a lot of use. Before we look at any of the rules associated with non-right angles, we need to learn some conventions. So a convention is just a way of doing things. So in triangles, the convention is to label sides using a lowercase version of the opposite angle. So we should be familiar with having points on a diagram labelled with capitals. So this point here, this vertex is A, this point here is B, and this point here is C. And they've all been labelled with capitals. If this is point A, this line here, this side of the triangle, is lowercase a. If this is point B, going straight across the triangle, I've got this side here, this lowercase b. And if this is uppercase C, this side here, the one directly across from it, is lowercase c. We need to know these conventions, and we need to know how lowercase and uppercase a are connected to help us use the rules. Right, here are the rules in question. We've got something called the cosine rule, something called the sine rule, and we've got a formula for the area of a triangle. We do not need to commit these things in the white boxes to memory. These formulae are given to you on your formula list. What we do need to learn is what I've got in these black boxes here. These black boxes are the situations that you would have to use each of these rules in. And today we're going to concentrate on the cosine rule, this first version of it. So here we have it here just on its own. This is used to find a side when you know its corresponding angle and the other two sides. So if we have a look at what this is describing, it's telling us we can find a squared. So we can find the length of this side here if we know b squared. So if we know this side, and if we know c squared, this side, and again, we've got this BC appearing again, so this is the same sides, and we need to be able to find the cosine of angle A. So here, this angle in here. So what we're looking for to help us use the cosine rule, well, so we can actually use the cosine rule, is this sort of setup. We're looking for two sides and the contained angle. So this sort of V shape here. So here we have a very typical problem. Find the length of side marked D. Now, I've written down my cosine rule here, and I suppose the first thing we need to not worry about is the fact we're not working with A, B, C, we're working with D, E and F instead. The letters themselves don't matter, they are just labels. If I wanted, I could totally rewrite the cosine rule with different letters. I could say D squared is equal to the other two sides squared, E squared plus F squared, minus 2, well I've got 2BC, so it's going to be 2EF here, times the cosine of A. So A, remember, corresponding to the side we're finding. So if I'm finding side D, I need to know angle capital D. And I mean, this is exactly what we've got here. E is going to be this side here. F is going to be this side here. And this angle in here is the angle D. Now, you don't need to rewrite this rule using the letters that have been given. What we could do is we could skip straight to this step. I've written down my cosine rule and I'm going to plug in the information. So I want to find side D. So D squared equals one of my sides squared, 10 squared, plus my other side squared, 6 squared, so I've just used these two, minus 2bc, so minus 2 times one side times the other side, times cosine A. So if I am finding side A, angle A is the one opposite it. So if I'm finding side D, angle D is this 47. So the cosine of 47. Now, most of the time you're going to be working with a calculator here, so don't worry about evaluating all of these little bits individually. A half-decent scientific calculator will handle that all in a oneer. So D squared equals. So I've typed that all into my calculator in a oneer. I've written this as brackets here, but I've typed it in with multiplication, just because I think it's a little bit easier, a little bit neater to write that with brackets, but you can write it as I've typed it there. So D squared is 54.16, so on. Now, it's important to realise this side is not 54 centimetres long. That is D squared. So to find D, I'm going to have to take the square root of this value. So again, sensible use of your calculator. You can use your answer button to help you out with that. So that'll give me an answer of D equals 7.359 so on. It's very typical because this is a calculator question where you're pretty much every time going to get a awkward big long number. This is usually there'll be some rounding associated with this, so this is a good opportunity to practice your significant figures or decimal places. So I'm going to round this to 3 significant figures, so 735. The 9 is going to round that up to 7.36 centimetres. So it's a very straightforward example of how to use this. If we are trying to find a side there, we need this V setup of 2 sides and the contained angle. Right, a slightly wordier question here. So we've got a runner sets off from point B and jogs north for 400 metres. He then turns 130 degrees clockwise and runs a further 300 metres to point C. What is the distance? What distance is the runner now from point B where he started? I.e., what is this distance here? So we're trying to find this distance on the diagram, one I've marked with a little X. One thing to note here, this idea of turning 130 degrees clockwise. This 130 is a bearing. We're going to see a lot of bearings when we're doing examples here. So just remembering that bearing is measured from north in a clockwise direction. We've been lucky here in that the text has been represented in a diagram, so we've not needed to draw this from scratch. If you're doing a question, I would always be making a sketch here so you can add some information into it. Right, this is the cosine rule here. I've got 2 of the sides. I'm trying to find the third side. So what I really need is I need this angle in here. So this is where this idea of north and bearings comes into it. This line here is a continuous line because he's ran north and then this line is still pointing north. So 2 angles on a straight line will need to add up to 180. So this angle in here has to be 50, since 130 off of 180 leaves me with 50. So I've got everything I need. I've got this classic V shape with a contained angle. So I can start substituting in my values. The side I want to find, a squared, right? Well, that's x squared, equals b squared plus c squared. I suppose I could be using these as b and c. So if this is capital B, this is lowercase b. 300 squared plus 400 squared minus 2 times b times c, so 2 times those two sides multiplied together times the cosine of a. Now remember, if this is the side we are working with, this is the angle we're using, so it's 50 degrees. Again, all of this gets plugged into a calculator in one go. So there, my calculator has given me x squared equals 95,730.9 blah blah blah, so on. Now remember, this is x squared, so I'm going to have to take the square root of this value. So again, sensible calculator use your answer button. The square root of my previous answer was 309.4. So x is 309.404, so on. Again, I'll round this to 3 significant figures. So 309. The 4 means I don't need to round up. So x is 309 meters to 3 significant figures. The runner is 309 meters from